If you take a tiny plastic star that costs about 5 cents, hold it under a desk lamp for 10 seconds, and turn off the lights, that piece of cheap plastic will somehow stay illuminated in the pitch dark for hours. It does not have a battery, it is not plugged into any wall, and it costs $0 in electricity to run. So how is an inert piece of bedroom plastic actively storing light and slowly leaking it back out into your room? Most people assume it works like a thermal sponge, soaking up heat and spitting out light. But if you touch a glowing star, it is completely cold. The real explanation is actually a bizarre quirk of quantum physics that happens on an atomic scale right inside your house. To understand how glow-in-the-dark stuff works, we have to zoom down into the microscopic world of the atom. Everything around you, from your smartphone to your own hands, is made of atoms. Orbiting around the nucleus of every atom are tiny, highly active particles called electrons. You can think of electrons as energetic kids playing on a stack of trampolines. Under normal conditions, they prefer to hang out on the lowest, safest trampoline level, which physicists call the ground state. When you shine a light on a glow-in-the-dark object, you are blasting those atoms with tiny packets of pure light energy called photons. When a photon smashes into an electron, the electron absorbs that incoming energy and instantly leaps up to a higher, wilder trampoline level. Scientists call this high-energy condition the excited state. Now, electrons hate staying up in the excited state for long. It is chaotic and unstable. Naturally, the electron wants to drop right back down to its comfortable ground state. But physical energy cannot simply vanish into thin air. To jump down to a lower level, the electron has to throw away the extra energy it absorbed. And it does that by spitting out a brand new photon of visible light. This basic process of absorbing light energy and shooting it back out is known as photoluminescence. Now, here is where a giant puzzle pops up. If you shine a bright flashlight at a regular sheet of white paper, the electrons in the paper absorb energy and drop back down almost instantly. The moment you turn off the flashlight, the paper turns completely dark in less than 1 nanosecond. So why does your cheap plastic ceiling star keep shining for 4 or 5 hours after you hit the light switch? The answer comes down to a critical split between two different types of glowing: fluorescence and phosphorescence. Fluorescence is the fast, impatient kind of glow. Think of neon highlighters, fluorescent markers, or white clothing under a black light at a bowling alley. Highlighters absorb invisible ultraviolet light from the room. Their electrons leap up to an excited state, and then they drop back down in less than 10 nanoseconds, emitting bright, visible light as they fall. But as soon as you turn off the ultraviolet black light, the glow vanishes instantly. There is no energy storage at all. Phosphorescence, on the other hand, is the patient, slow-burn glow that powers ceiling stars, glowing watch dials, and dark-glowing toys. When light hits a phosphorescent material and kicks an electron up into an excited state, something extremely unusual happens on its way back down. Instead of falling straight down to the bottom level, the electron undergoes a subtle quantum spin flip. Scientists refer to this process as intersystem crossing. By flipping its spin, the electron enters a special trapped energy level called a triplet state. You can imagine it like taking an elevator down from the top floor of a building, but getting stuck in a locked middle floor waiting room. In quantum mechanics, escaping from this particular waiting room is classified as a forbidden transition. That does not mean it is strictly impossible, but it is extremely improbable and takes a long time to happen naturally. The electron is essentially trapped behind a quantum energy barrier. Because escaping is so difficult, the trapped electrons cannot all fall back down at once. Instead, they trickle out slowly, one by one, purely by chance, over minutes or even hours. Every single time one solitary electron finally overcomes the barrier and drops back to its ground state, it releases a single photon of light. When you have trillions of trapped electrons escaping in a slow, steady trickle over several hours, you get that soft, comforting glow on your ceiling all night long. If you grew up with glow-in-the-dark toys in the 1980s or 1990s, you might remember that they were pretty weak. You would charge a plastic toy right next to a 100-watt bulb for 10 minutes, turn off the lights, and get maybe 15 minutes of dim green light before it faded out. That was because older products relied on a chemical compound called zinc sulfide. Zinc sulfide has a very small electron waiting room, meaning it can only store a tiny amount of energy and leaks its electrons very quickly. In the mid-1990s, Japanese researchers revolutionized the industry by developing a compound called strontium aluminate. Strontium aluminate is essentially a supercharged electron storage locker. It can trap up to 10 times more light energy than zinc sulfide, and it releases that energy up to 10 times brighter and for a much longer period of time. Just 1 minute of exposure to natural sunlight can keep high-grade strontium aluminate glowing brightly for over 12 hours straight. Today, it is used in professional emergency exit routes inside high-rise buildings, dive watches, and high-performance safety gear that must remain visible during power outages. At this point, you might wonder, is there a material that glows forever without ever needing to be charged under a lamp? The answer is yes, but human history learned the hard way that this capability came with a horrifying downside. In the early 1900s, watchmakers wanted to sell wristwatches with glowing numbers that never needed sunlight. To do this, they mixed regular glow powder with a newly discovered element called radium. Radium is intensely radioactive. Instead of needing light bulbs to push electrons up into excited states, decaying radium atoms constantly blast nearby phosphor molecules with high-energy nuclear radiation. This continuous nuclear hammering keeps the electrons excited perpetually, creating a dial that glows brightly day and night for years with zero light input. In the 1910s and 1920s, young women known as the Radium Girls were hired to paint these watch dials. To paint tiny, precise numbers, they were instructed to lick the tips of their paintbrushes. Unaware of the toxic hazard, they ingested tiny amounts of radium every single day. Because radium is chemically similar to calcium, their bodies absorbed the radioactive material straight into their bones. This led to catastrophic health consequences, radiation poisoning, and severe bone decay. That tragic historical lesson led to strict industrial safety laws and the phase-out of dangerous radioactive consumer goods. Today, items that require perpetual glow without light charging, like high-end military compasses or tactical watches, use sealed microglass tubes filled with tritium gas. Tritium emits very soft radiation that cannot penetrate human skin or the glass casing, safely exciting the internal coating for about 12 to 15 years before slowly fading. So, what about glow sticks? They do not need to be charged under a lamp, and they are completely non-radioactive. How can a plastic tube light up a dark trail or a concert venue out of nowhere? That brings us to chemiluminescence, which is glowing powered purely by chemical reactions rather than light absorption or radiation. Inside a standard glow stick, there are two separate chemical liquids kept apart by a delicate glass capsule. One liquid contains a fluorescent dye and an organic phenyl oxalate compound, while the inner glass vial contains hydrogen peroxide. When you bend and snap the outer plastic stick, you break the thin glass tube inside. The two liquids mix together, starting an immediate chemical reaction. This reaction breaks chemical bonds and releases raw chemical energy that slams directly into the fluorescent dye molecules, driving their electrons into excited states. As those electrons drop back down, they release that chemical energy as vibrant, visible light. Because chemiluminescence relies on a finite chemical fuel supply, The glow stick eventually runs out of fuel once all the molecules have reacted. Once it goes dark, you cannot recharge it under a lamp. However, you can manipulate the physics with temperature. If you toss a freshly cracked glow stick into a freezer at 0 degrees, the cold temperature slows down the chemical reaction, dimming the light, but extending its total lifespan across 2 or 3 days. If you throw it in hot water, the chemical reaction accelerates, producing a super bright glow that burns out in just a few minutes. Humans may have invented glow sticks in the 1960s, but nature beat us to the punch by millions of years. Bioluminescence is simply chemiluminescence performed inside living creatures. From glowing fireflies on warm summer nights to deep-sea anglerfish navigating pitch-black ocean trenches 1,000 meters under the surface, biological glow is one of nature's greatest survival tools. Living organisms produce light using a natural compound called luciferin, combined with an enzyme called luciferase. When luciferin reacts with oxygen in the presence of luciferase, it releases light with astonishing efficiency. Traditional incandescent light bulbs convert less than 5% of their electrical energy into actual light, wasting over 95% as heat. A firefly, by comparison, produces cold light with nearly 100% energy efficiency, generating almost zero heat in the process. If a firefly produced heat at the same rate as an incandescent bulb, it would literally cook itself from the inside out. Today, understanding how things glow is doing far more than decorating bedrooms or illuminating dark ocean depths. Biologists have extracted green fluorescent proteins from glowing jellyfish and implanted them into human cellular research. By fusing these glowing biological tags to specific proteins, scientists can watch living cells under a microscope in real time. They can track how cancer cells spread through tissue, watch viruses attack host cells, or monitor how experimental drugs treat diseases at an atomic level. So the next time you turn off your lights and watch those humble plastic stars shining on your bedroom ceiling, take a second to appreciate what is actually happening. You are not just looking at a cheap piece of molded plastic. You are watching a real-time display of quantum physics, where trillions of trapped electrons are slowly escaping their molecular waiting rooms and releasing tiny packets of light, step by step. Before you head off to charge your glowing gear, I want to know, what was the absolute weirdest or coolest glow-in-the-dark item you owned when you were growing up? Tell me your story in the comments below. If you found this video fun and learned something new today, hit that like button, share this video with a friend who loves science, and subscribe so you never miss another deep dive into the hidden machinery of our universe.